All right, so our next speaker is Tim Genewein. We'll be talking about learning universal predictors. Yeah, thank you. So let me just get this. Yeah.
Wait, I mean, is this on the recording? But is there a way to hide the menu?
Yeah, this is. Yeah, there is a way.
Yeah. Or yeah, maybe just move it.
Yeah, then there's. I don't know what was the way.
Maybe just move it to the very top. That should be fine. I can just. I think the slides are in full screen.
Yeah,
yeah, is it good or you want full screen? You said, yeah.
Yeah, full screen. I mean, I'll just move the. I think it's fine. Yeah.
Yeah, I think it may disappear on its own.
Yeah. Just gonna see if I can move. Thanks. Okay. Hi everybody. I'm Tim. I'm currently a researcher at DeepMind, and you can see all the people from Google don't know how to use Zoom. And I've been at DeepMind for 6 years, and I'm mainly interested. My background is in computational neuroscience, and so I was interested in trying to apply some of the techniques and tools there to understand how neural networks work, and also sort of what the limitations are. And then through various circumstances, I ended up working with Marcus in a team where I got exposure to algorithmic information theory and IXI. And the work I'm presenting here is an outcome of this period where we looked into the question of whether it's possible, at least in theory, to sort of learn universal predictors with neural networks. And there we go. And so the talk is sort of, says roughly 3 parts. First, I want to talk about memory-based meta-learning, which is a view on how neural networks are trained. And if you formalize that view, you can show theoretically, and we also show that in practice, that you get a very nice general recipe for learning Bayesian predictors with neural nets. And then looking at developments with large language models and large neural networks, there is a question of whether they are sort of starting to become increasingly universal predictors. And I'll just briefly tease some results we have there. And the question we had that triggered this whole project was, how far can this really be pushed, both in theory, and it's mainly a theoretical works, but to sort of show that it's not just completely empty theory. I'll also show some toy experiments at least. And this is the team that was involved in the work, and a particular shout out to Jordi, who was mainly driving this project. Okay, let's talk about learning Bayesian predictors first. And the recipe is quite simple. What you see here on the slides is the so-called meta-learning loop, and it has 3 steps. In the first step, you sample a task from some task distribution p tau, and then you generate data from that task distribution, in this case, sequential data. And typically, you don't just generate one sequence, you generate a whole batch of sequences, and then you update your model parameters, which is now your neural network, to minimize sequential prediction error, aka log loss. And you keep iterating, and then what you can show in theory is that, first of all, to the meta-learner, the data distribution, that the meta-learner doesn't observe the task, it only sees the sequences. And so the data distribution looks like it's this mixture over all tasks and sequences. And you can then write down the excess log loss, which is sort of the suboptimality in prediction, which is simply the expectation under this data distribution of the prediction of the model that you're trying to learn versus the prediction error versus the optimal prediction error, which is given by the mixture predictor. And this, of course, reduces to the KL divergence, which is non-negative, and more importantly, equal, applying minimal loss, if your neural network predictor predicts according, or the predictions are in line with the mixture predictor. And so if you put this together and you assume that the network can actually implement this solution and that stochastic gradient-based optimization converges there, then you get a network with fixed parameters. So the weights are frozen now, and you can now feed in sequences and partial sequences. And then if we look at the predictions that this network makes, they're equivalent to the mixture predictor, which computes, of course, adaptively computes the Bayesian posterior over all tasks given the observations so far. And so it's a bit strange maybe at first, but you get this model with completely frozen weights, but it implements an adaptive prediction algorithm that is sort of purely lives in the model's in activations. Does it work? Yeah. So we tried this over a number of papers and a number of examples where the focus was to really see if we can reach Bayes optimality. And so we have some older work. You can see the references down here, and they're sort of color-coded. So in this older work, we tried lots of IID examples. We tried Peter Bernoulli distribution, Dirichlet categorical distributions. We also tried Gaussian distributions. Theoretically, you can also extend this to decision-making. And we have some work here on two-arm bandits with Bernoulli and Gaussian rewards. And so in all of these cases, you can train networks to behave Bayes optimally after training. We later moved on to more complex distributions, particular piecewise stationary distributions, where the Bayesian algorithms are already quite involved. So there is one called partition tree weighting from Joel Van Ness, who is also, or who was in our team at the time. And there's an older algorithm by Franz Willems that deals with piecewise stationarity. And then the final example, which I'll show in 2 slides, is variable order Markov sources, where Marcus already mentioned there is this very nice algorithm also by Franz Willems called CTW context tree weighting. And just as a teaser, if you do this and you look at what neural networks are doing, one of the predictions, of course, is that they need to keep track of sufficient statistics in their internal state. And so what you see here is a predictor trained on coin flips of random of sequences from coins with random biases, so like a beta Bernoulli predictor. And each dot is the recording of an internal state, and we feed in trajectories of these, lots of trajectories from these random coins. And this is just a 2D PCA of the internal state. And if you color it with the step index within the sequence, you find that one of the 2 dimensions corresponds very well. So top plot is a transformer, bottom is an LSTM, corresponds really well to the step. And the other dimension corresponds very well to the ratio of heads and tails observed so far. And these are exactly the 2 sufficient statistics that you would need to keep track in for Bayes optimal prediction here. Okay, some maybe first signs towards universality is looking at variable order Markov sources. And as I said before, for binary variable order Markov sources, there is this very nice and very elegant algorithm, context tree weighting. And so what we did is we basically trained, we meta-trained a neural network on sequences from these variable order Markov sources. So we first sample an order Markov chain, and then we sample sequences, observations from this chain, and we minimize log loss. And what you see here in red is the neural networks predictions, and in blue is CTW, which is Bayes optimal in this case. And in the top plot, these little blue dots are now the binary observations. And you can see that the predictions in red of the network and of CTW, they overlap very well. And we then turn this sort of prediction error into a cumulative prediction error, but we also subtract sort of the optimal prediction, which gives us this cumulative regret. which is basically just the cumulative prediction error over the whole sequence. And that's the main metric that we usually look at. And if you do this over a lot of sequences, in this case with a maximum context length of 24, you get the result here on the right, where the different groups of bars are different kinds of neural architectures. The y-axis is the mean cumulative regret, and the dashed line is CTW. So this is sort of optimal performance for this data. And you can see that the large networks in this case, particularly the LSTM and the transformer, match the performance of this predictor very well. Small caveat, when I say large for this experiment, by modern or LLM standards, these are tiny networks. What this plot shows is that the network size does matter. So you need to reach a certain scale for things to really work out. And I think the networks here are 3-layer LSTMs and 6-layer transformers with a width of 128 or 256. So again, tiny networks by large scale standards. You can also look at length generalization, which is quite interesting. So we usually train on sequences of length 256, but you can just evaluate on much longer sequences. And what you can see in this plot here is that especially the yellow and the red line, which are LSTM and sort of an RNN variant, and also this dark blue one is an RNN variant, they generalize relatively well, whereas the transformer doesn't deal really well with length generalization. And we have some ideas on why this is. It might be related to positional encoding, but it's also something we've observed a number of times in other experiments. Feel free to ask me about it in more detail. Okay, so now we have sort of this recipe, which we've explored to train Bayesian predictors. And all it basically says is, well, you need to minimize log loss over this meta distribution. Now, looking at LLMs, what they're doing is minimizing log loss, but over maybe a slightly different kind of distribution, where they're not doing this explicit meta-learning recipe. And so our focus was on doing these small-scale experiments where we have a tractable Bayesian predictor, so we can really compare precisely. And we also have full control over the data generation statistics. And so these two things are usually not fulfilled or are not fulfilled at LLM scale. So how could we get any sense of whether they're getting more universal or getting better? And like Marcus teased before, we can look at compression performance. And so the idea here is that, well, okay, we don't have a known Bayesian predictor. We don't know the optimal performance, but we can now take out of distribution data and just see how well these networks compress. And what we did in particular was we took an LLM. Back then, this was Chinchilla. And we feed images and audio data as byte streams into the network, even though the network has only been trained on text. And then we use the predictions, next token predictions, to do arithmetic encoding for lossless compression. And we compare that, the compression that we get with this neural network compressor against standard compressors like gzip and LZMA2. And what you find when you do this, just look at the green boxes. So the columns here first is text data, is 1 GB of Wikipedia. Second column is 1 GB of images from ImageNet. And then the third column is 1 GB of audio data. On the top, you have general purpose compressors, but you also have domain specific ones like PNG for images and FLAC for audio. And down at the bottom here are the Chinchilla models. And sort of even the smallest model already performs really well. And then the largest, the 70 billion parameter model in this case, somewhat unsurprisingly compresses text really well. That's what it's been trained on. But it even compresses images and audio data better than the standard compressors. So that is at least a sign that the network has learned some statistical and algorithmic patterns that are generally useful for compressing data. Now, there's a small caveat. I'm not really going to go into details, but please ask me about this work too. What we're looking at here is compression rates without taking into account the model size. And like Marcus said before, if you want to compare compressors, depending on what you're after, you need to take into account the model size. And we have a whole lot of follow-up work where we basically show that this is also possible if you take into account the model size and you make compressors smaller. But what we find in this case is, sorry, if you make neural networks smaller, what we find in that case is that we don't really see this transfer. So the networks at that size have sort of on the order of tens of millions of parameters. And at that scale, we don't see this emergence of this transfer. So something happens between this millions of parameter scale and billions of parameter scale, which we at least haven't really looked into yet. Okay, coming back to the, yeah. Yes.
What is exactly going to, when you're compressing images, like you're tokenizing, I suppose,
yeah, so in
the byte string or the bit strings.
Yeah, in this case, we did something very naive. We just we converted to we first converted a color image to grayscale, and I think we take 8 or 16 bits. I don't remember for that conversion, and then we just flatten the image in a particular way, which destroys all of the spatial relationships between pixels, right? And then we just feed this byte stream in 2048 byte-sized chunks into the transformer. And feed the predictions into an arithmetic encoder for compression.
You're not limited by the context window size.
Well, we are. So in this case, I think the context size was 2048. Yeah. Which means I think for some of the images, less. I'm not even sure if the whole image. So we basically reduce it to one channel, right? But even in this case, I think the whole image may be larger than the context size. So potentially there would be gains from having larger context with that capture more long-range correlations. There is some follow-up work, and I think something coming out at NeurIPS, or at least being under review, that does this in a more sophisticated fashion. Yeah. Okay. Any other questions so far? Good. Okay, so now coming back to seeing how far this can be pushed. And I guess the first observation is quite simple. If looking at this meta learning loop, well, we could just meta train over all programs, right? So a program is a task. The data generation is easy. We don't need to sample. We just run the program through a Turing machine, which gives a deterministic output, a universal Turing machine. And then we minimize sequential prediction error over this program outputs. And we do this with a large set of programs. And in theory, this should give us a Bayesian sequential predictor over the space of programs. And you could say, well, how do we get Solomonov's prior? And the only way the prior enters here really is the way we sample from the task distribution. And, okay, so next slide. And so there's a very easy way or there's literally a construction for Solomonov's prior that depends on sampling random strings and feeding them through a UTM. So we could use that in principle. The questions that we asked in the paper are a bit more involved, I guess. First of all, there's a problem with this naive sampling. So how do we more practically generate the training data for approximating Solomonov induction? Then on the more practical side, transformers want fixed length sequences. How do we deal with that? And then finally, perhaps even more practical, can we use more interesting program distributions than just sampling randomly without losing universality? And all the results are in the paper that is shown here on the slide. Okay, first problem, sampling training data. As I said naively, this is literally the construction, right? Or one of the constructions for universal probability is to just sample random bits and feed them in a UTM, a monotone UTM, and record the program output. And that naturally ensures consistency with Solomonov's prior. The main issues here are that programs may loop forever and outputs can have infinite length, and that we are dealing with a semi-measure that has probability gaps. And really what we would want is a computable procedure that produces a finite data set without losing this consistency. And again, we tried something very straightforward here, which is just to take now a Turing machine, but to overcome the limitations, we just run it for a fixed number of steps or until the output exceeds a certain maximum length. And that also implicitly limits the program length. I mean, programs can't have more than a length of S steps. And now we can, of course, formalize this, and the formal notation here gives us sort of a computable Solomonov prior that is limited in exactly this fashion. And what we show in the paper is that if you now take these limitations and you let them converge towards infinity, that we still have consistency and converge towards a universal prior. There's another small caveat, which is that we use a normalized Solomonov prior, which gives a proper measure and not a semi-measure. That also makes the method more practical. And then I said there's sort of two more issues that we address. The first one is having a fixed context length, and that's quite easy. We just pad all sequences that are shorter than this fixed length with a special padding symbol, and we mask the loss on these padding tokens. The second one is more subtle, and I would say is really just the start of, well, we're really scratching only the surface of what's possible here, but ideally we would like a non-uniform distribution of our programs to sort of have more interesting programs for meta learning, because many of the programs, of course, depending on the universal Turing machine we use, I'll show it in a bit, but many of the programs we get, they don't output anything, or they make very, very short outputs. And what we prove in the paper, which we then found out was also independently discovered by Starkenberg in 2017, is that you can actually skew the distribution for sampling programs almost arbitrarily. There's relatively mild conditions. You basically need to ensure that all programs still have some probability mass. And there is a sort of like an entropy condition, but it's really, from a more practical viewpoint, you can come up with almost arbitrary program distributions. And putting all of this together, we now have a practical data generator for meta learning that's computable. All steps are finite. It's consistent as we increase mainly the number of steps on the Turing machine and sort of the output length. We converge towards a universal distribution. It has no probability gaps because we have a proper measure. And we can even use non-uniform program distributions. And they can really, they can be non-IID, non-ergodic, non-stationary, non-atomic. So there is a lot of flexibility here. And then assuming we can generate the data, which of course requires compute, and that the neural network can realize and converges to the solution, we could meta train towards universal prediction. Does it work? Well, so we ran some simple experiments where we took a variant of the brainfuck UTM, which is very simple UTM. In our case, it has 7 instructions. We chose the output alphabet size to be 17 because we compared against some other data set where the alphabet was 17. We ran it for 1,000 steps with 200 memory cells, and the maximum output length is 256 symbols. It has a read-only input tape, a working tape, write-only output tape. So it's really simple UTM. And there's some additional optimizations that we do for our use case. And you can find this UTM on GitHub if you're interested. And we also came up with a non-trivial but still loose upper bound for estimating the Kolmogorov complexity and then the Solomonov log loss by shortening programs via various heuristics. And just to give you an example, you can see programs in this modified brainfuck language here with the corresponding outputs where each color corresponds to one of the 17 symbols. And as you can see, you get somewhat interesting patterns. Most of them are repetitive or relatively simple, but some of them are quite complex, as you would expect. And now when we train on these distributions, so we collect a large data set, we meta train a neural network or a couple of different neural networks, and we look at regret. We now don't have an optimal baseline to compare against. We do have this naive baseline, which we get by shortening programs using various heuristics as much as we can. And at least what we see is that, again, network size matters. So predictions get better as networks get larger. And in this plot, in the middle plot or the right plot, we show the accuracy with which, so this is taking the top prediction and comparing whether that is actually the token that comes next in the sequence. And we see that the accuracy actually is really high. So the predictions are quite good.
About this accuracy, is that not just dominated by a bunch of pretty simple trivial?
Yeah, Yeah. Of course, it depends on the data distribution, and many of the symbols are probably quite easy to predict. But if this accuracy were down at 0.6, I think it would be much worse. We also look at length generalization and get a quite similar picture. And then maybe the most interesting one is, well, what happens if we now take this neural network and we evaluate it on other data, or in modern ML speech, this would be zero-shot in-context learning on out-of-distribution data. So we have one set of tasks, which is 15 different algorithmic tasks spanning the whole Chomsky hierarchy. So these are regular context-free and context-sensitive tasks. And you can see a similar qualitative picture, where in this case, for the accuracy, the naive predictor is just predicts basically randomly, uniformly between the tokens of the particular task, which in this case amounts to a random chance of predicting the next token of 0.3. So we beat this naive predictor, but the margin is now probably a lot smaller than it used to be on the UTM data. And we can do the same with these variable order Markov chains, where we see a similar picture. So there is clearly some non-trivial transfer, and I think some promising signs, but we're also still far, or likely still far, from being optimal. I'm almost out of time. So just to mention it, we also, at the very end of the paper, we investigated coming up with some heuristics to make the program generation more interesting, because most of the programs that we generate are regular and are thus maybe quite easy to predict. And so we come up with some heuristics to make programs more interesting, with which we filter programs, and then we learn a second-order Markov chain to generate such programs, and that sort of increases this interestingness by significant 2 orders of magnitude at least. And these are things like more likely outputting something, or less likely producing a loop, or producing symbols that cancel each other. And yeah, again, if you're interested in this, just let me know. We didn't train, unfortunately, we didn't train on this heuristic. It was something we added very late to the paper, and it didn't make it into the paper. But it would still be interesting to run these experiments at some point. Okay, wrapping up, are we done? Well, not really. I mean, we've just started. There's lots and lots of practical issues and questions. There's many ways to improve efficiency and practicability, maybe in ideas for finding better neural architectures. But the results show that, at least in theory, this meta-training view could be a viable path for approximating increasingly universal predictors. And that sort of means that, maybe training gigantic networks on minimizing prediction error on a large and complex data set is not such a bad idea after all. It's also possible to make practical progress. Stuff runs, and you will find something interesting. And maybe the final takeaway is that tracking general compression performance of LLMs might also help get some insight into whether we're sort of approaching certain forms or notions of broad notions of universality. Concluding, so we really only just started looking at generalization or transfer to other tasks. So there's a lot more to be done. One question is, could pre-training on the outputs of these random programs really help with generalization? And maybe someone in this room should really look into this, or might actually speak after me and look into it. Another question which we haven't touched at all is, how would you combine such a pre-trained inductor with search to push the performance ceiling and maybe amortize the results back into the network? And finally, maybe as a disclaimer, our work isn't really meant as the recipe to now train a Solomonov inductor, but is a starting point to sort of really bridge the gap between modern ML practice and deep insights from AIT. And the good news is, as networks get larger and more universal and optimization gets better, the theory gets sharper. So it's maybe a bit of a bitter lesson too. And so you could say that the overlap between AIT and ML has never really been larger. So I think it's a good time to start bridging this gap and really working on this. That's all. If you want the main reference, it's on there. And yeah, if you have any questions at any time, just reach out. Yeah.